let's see. Okay, so you're asking about if we have, say, this ball that's impacting the pendulum. Okay, so basically what happens, like you said, is beforehand, most of the time we have that this thing would be still, right? So this guy right here, the pendulum doesn't have anything. But, we can always make this where at the beginning we can talk about the IG of the rod, right, times its initial omega, plus then we'd still have an M of the rod times velocity of the center mass of the rod, right, times its perpendicular distance. So this would be all the rod, okay, beforehand, right? And then we can do plus I of the sphere, right? So this is going to be S, and this is going to be the rod, times omega, and that's going to be of the sphere. So it could be that sphere had its own rotation going. Mm-hmm. Right, and then we do a plus mass of the sphere times the velocity of the center of the sphere times d perpendicular. Okay, so this would all be for the sphere. Is that all right?
Yeah.
Okay.
Quick question.
Yeah.
Those perpendicular distances, where are they to?
Yeah, that's great. So what do you have to define first? So let's say this is point O, and down here is point A. So if I'm doing angular momentum, what do I need to say first?
I don't know, like what point it's rotating at?
Exactly. So you do know, right?
Okay.
So yeah, you have to define, just like we always did for statics, I have to say what point am I summing moments about. Okay, so in this case, I'm going to do it about point O because it's a fixed axis of rotation. Mm-hmm. Okay, so initially, does this make sense? So the IG omega, so for the rod, the question is, because this rod could be, say, swinging down, like this maybe to hit it. Do you understand? Does that make sense?
Yeah.
Okay, and then that would be about the rod's G. Does that make sense?
Yes.
Okay, and then its center, right? So if we do out our nice diagrams now, right, then here we would say, okay, I could have some sort of initial omega, and let's say I knew it was going that way. So that could be like an I rod omega, right? Mm-hmm. And then its center mass would also have some sort of an M R V R, that's its center mass. Is that okay?
Yeah.
And then I could also draw in right here, I could say, okay, this is my M S VS, right, V bar S. And I could even say, like, if this thing could potentially have some sort of its own spin, right, its own omega. We haven't really done that much before, right?
Yeah.
But it could. Okay. Then what do I put for my next part of the diagram?
The impulses.
Yeah.
Forces.
So what are my impulse forces here?
So there's the ball hitting the rod.
Yeah. So I'm going to put. Yeah. So I'm going to actually. Sometimes I do like this. This is kind of what I probably like the most when I do it. Is like an F delta T, and that shows that those two are equal and opposite. Mm-hmm. What else do I have?
Then there's also the reaction forces at O.
Yeah. So I do like an OX delta T. And I do an OY delta T. Okay? And then in the end, right, now, here's where the part comes in where I think it can get a little tricky for people is, let's say that these are going to stick together. Okay? So if you looked at, when we did this, the problem, did you look at the solution to the in-class problem we did on Monday?
Yeah.
Okay.
Yeah.
So for those, right, now you have, again, because we can say now, right, now we would do these, some of the whatever moments about O dt, right, but if I look up here, right, then about O, what are my sum of moments?
Just the impulse force?
Yeah, but what's these two will cancel out, right?
Yeah.
And then if I sum moments about O, what happens to those?
They also cancel out, so they're zero?
Yeah, they don't quite cancel out. I would say that, you know what I mean? Yeah, there's no perpendicular distance, so those forces don't exert a moment. Mm-hmm. Does that make sense to you?
Yeah.
Okay, cool. So then what happens is really I have the exact same thing all over again. So now I can say IG omega, but I'm not going to say prime plus MR VR D perpendicular, right? But now this is going to be a prime, and that's at the center mass of the rod, right? And then I have plus this IS omega S of the sphere plus MS VS D perpendicular, where that's a prime and that's a prime. Okay, so it's the same thing all over again, but now these are after the impact. Okay.
Quick question: where this isn't like the Monday problem where they stick together. This is just it bounces off the rod.
No, these are sticking together as well. We said we wouldn't do ones because if it bounces off the rod, we'd actually have to have an E relationship, a coefficient of restitution.
Okay.
So this is just a general type of problem, that.
Well, so if it's sticking together, is it not like the same concept of like translation impulse momentum where you just combine the masses and whatnot?
No, because the distribution of mass matters, right? We've done that a couple different ways where you can't just add the mass. There's a lot of background noise right now, so I don't know if people, Sydney, you might need to mute yours for a second. Thanks, yeah. So there's, you can't just combine the masses because, in this case, the mass is down here for the ball. Right, so you can't just add those together. You have to actually treat them differently. So, if you have like this one right here would be for the rod again, but just like we did with that one problem on a quiz, I can actually write this out as I-O omega prime, right? Because remember we said that down here, right? That's essentially what is VR prime? Well, that's just going to be R omega, right? And so this thing really just translates to L over, if that was a slender rod, that would just be L over 2 times omega times the D perpendicular is L over 2, right? So that's, what is I omega? Or IO is just is MD squared plus IG, right? So I went over that kind of fast. Does that make sense, Sydney? That's actually quite related, I think, to what you were asking about with I you take it about originally.
Yeah, that makes sense.
Okay, so now let me go back to Abdullah's question, and this is also tied to Sydney's, where now we look at this part here, right? So in general, we've been having things that hit it like a ball, right? There is a problem you could look at, I think, in the book where instead of the ball going, it's like a javelin, right? So then you would have to actually say that this thing would have an omega. So there's a problem where now instead of the ball hitting, it's a javelin. Okay, so now that would have an I, whereas pretty much the bullet doesn't have an I, the thing hitting like this, that doesn't have an I. So for all our problems we worked, we said that IS is basically negligible. But it should make sense to you. It could just be 2/5 mr squared if it was a sphere.
Wait, why would we cancel out the sphere's moment of inertia?
Because we've treated it as a particle for all the problems we've worked, except for that one we did on Monday, right? And that full solution's posted for you.
Okay.
Okay, so now the final part comes in to where you have to look and say, how am I going to treat this? Okay, so if it ends up that I'm doing like a bullet problem and the bullet weighs 2 ounces and the pendulum weighs 50 pounds, right, then what can I say about that term that I just highlighted? What would be true about this whole term?
0.
Yeah, it's essentially negligible, right, because that mass is so small. But if it's a problem like where the ball is pretty big that we've done, or that sphere, now I have to include it, okay? Well, if I look at this VS, right, there's 2 ways I can do it, right? The first is I figure out, well, VS prime here is equal to omega cross r, basically, right? Because VO is 0. Does that make sense to you, Sydney?
Yeah.
Okay, so I can go through and do it all that way, right? But if this thing is just kind of basically buried right into there at the very end, I could also even include this in my IO term, where basically I would just add the, I could also say I'm just adding really MS times how far away is that thing? Well, it's all the way down at L squared, right? So this could just go into part of an overall big old IO. Okay, so that would be the IO of this whole thing together, where I have both the bar and that sphere together. So there's kind of multiple ways you can do it that all give you the same answer.
Okay.
Are you sure?
Yeah, so it's like you can combine them,
But
or
you don't.
you could do them separately. Either way works.
Yes, you either combine them all into one big IO, or you just leave them like what I've done kind of over here on this side. You could also just leave them and then use kinematics, and you still get the same thing. So again, it's all related back to that quiz that I turned back to you, where you proved to me that for energy, right? If you remember that one, I had you prove to me that 1/2 IO omega squared is equal to 1/2 Ig omega squared plus 1/2 mvg squared, right? It's the same basic concept here.
Mm-hmm. Okay, thank you.
You're welcome. Okay, Sonia, I think you signed in next. Are there any more questions first about what we have up here?
My question is sort of still related to this.
Okay, go ahead.
So for like the question that we did on Monday and also the quiz on Friday, the velocity of the ball or sphere that impacted was not like horizontal or vertical, it was at an angle, and I wasn't sure how you would figure, like you would know where the direction of that velocity, I guess.
Yeah, so in those cases, right, if you have something hitting like here, right, is how one of them was, right? So for one of those, for the quiz problem,
it was like onto a plate. Right?
Yeah. Sorry, I'm thinking of a different one. So there's some other ones where there's a plate. Did I give you a homework one like this? Yeah, we were doing it in class, right?
Yeah.
So there was one in class where it was going like this. So for something like that, it's still where, if you remember from the basic ones, it's either this type of term here, or we could also say it's R cross MVG. Okay, so for all of these, like in this case, your perpendicular distance is like this, right?
Mm-hmm.
So,
yeah.
But sometimes that geometry can get to be a little bit of a pain. So it's sometimes easier to just do like this, where R would be from here down to there, right? So from here to there, because we're talking about this moment that it's causing.
Yeah.
Does that part make all right sense?
Yeah, it's more in the after the impact, how in the impulse momentum diagram, you would know the velocity, like the direction of its velocity afterwards.
Yeah. So for this case, and the ones we've done before, since it actually sticks to it, right? So it sticks in there, and we're going to assume, unless I tell you somehow otherwise, that it's basically just going to stick at the point where it impacts. Okay. So now, if it's stuck right there, then remember we're just looking immediately after the impact. So we're not looking at it, 5 seconds later or anything. So right at that instant in time, this thing is just acting kind of like a pendulum, right? Because it's still fixed right there. So for that ball or bullet or whatever it is, its angular velocity is going to equal the angular velocity of the whole thing. Does that make sense? Because it's embedded in that plate. So that means its linear velocity is going to have to be still perpendicular to this thing right here.
Okay. So it's like tangent to the curve that
Yeah.
following.
Yep,
Okay.
exactly. So that doesn't mean it's still in this exact same line, right? It's
Yeah.
perpendicular to that plate. So let me see if I can do a new whiteboard page. So before I'm trying to decide if does anybody have questions about what I've got right there. I'm going to actually erase some stuff so I have a little bit more room.
Yeah. Well, I mean, I only had a question in terms of like the direction that you were saying right now, how it's like tangent, but I guess
Okay.
you'll be drawing some more about that.
Yeah, let me just get a little bit of space for us here. So give me 1 second here. Okay, go ahead, Abdullah. What were you saying?
I was just like, could you just clarify as to how the like finding that tangential velocity? You were saying that it wouldn't be this about like that same line of line of action of the initial bullet, and like it wouldn't be the same line of action of the velocity of the bullet initially.
Yeah,
So, like,
so let me show you a couple other sort of examples. So right here, let's say that we had the bullet or the sphere going this way, okay? And then it hits right, let's say it hits right at this point, right? So, and this is pinned up here. So if that's the case, then what's going to happen to the bar? How's it going to rotate?
like counterclockwise.
Yeah, so it's going to do like this. Oh, shoot, did my pen just go out again? Oh. So it's going to go like that, right?
Yeah.
So, okay, so if it's doing like this, what's the direction of the velocity of this thing?
I guess directly to the right.
Yeah, so it's going to be horizontal, right? So do you see how those two velocity vectors don't match up?
Yeah.
I just was worried that right here when I drew it that was a little bit confusing because those could be the same line.
Yeah, yeah. I mean, this clarifies it a lot more.
Okay, so let's even look at that one we did on Friday's quiz, right? Where I think this thing was down here, right? So it got caught right there.
Mhm.
And I think I posted this solution, didn't I?
Yeah, you did.
Okay, so basically now this thing's just falling, right? So remember we look at it right before the impact. Okay, so it's got some sort of MV going downward, right? So what's its perpendicular distance? And first of all, where am I, if this is like 0.0 and I don't know, that was like B prime and this was C prime, but we'll just leave them as B and C, right? Then what point should I sum moments about?
Oh.
Yeah, 0.0, because that's where our pin was, right? And that'll get rid of those reactions. So in this case, right, I've got a perpendicular distance that's just right there. Does that make all right sense to everybody?
Mm-hmm.
So basically my HO initial is going to equal, and I'm normally I would, of course, draw out all my diagrams and everything. So now I have an MV times that D perpendicular, which, like we said, is this amount right there. And if I do my typical type of axis system, right, then this is going to be a minus sign because it's going to go that way.
Mm-hmm.
Is that okay with everybody?
Yeah.
So this is before the impact. Now after, right, then that ball's going to be right here. Okay, so if I'm pinned at O, what is the linear velocity direction going to be of that sphere at cup C?
Could you repeat that?
Mm-hmm. Right. So here's my spheres right here at C. So after the impact, after it's caught in that cup, which direction is the velocity of point C immediately after the impact?
Just wouldn't it also be down?
It's like down and to the left.
Okay, and so it is going to be down and to the left. And how could I say that even more specifically?
Perpendicular to that.
Perpendicular to this line right here.
Okay.
Okay, and why is that? Well, because the velocity of this new C is going to equal where that is. It's like velocity of O plus omega cross R. So that's how you would do it, and I'd say omega prime.
Okay.
Okay, but hopefully with these, if you have this fixed point like where O is, you should be hopefully starting to get a little bit of a feeling for, hey, I've got rotation about a fixed point, so I know which direction any point on there is going to be, right? It's just going to be a tangent to that line connecting point O and whatever point C, right? So what if I landed here? Well, then it's going to be the linear velocity is going to be in a direction perpendicular to that line connecting those two.
Mm-hmm.
Okay?
Okay, yeah, that makes sense.
Daliana, can you hear us? Did you have any questions?
Sorry, couldn't figure out how to work it.
No problem.
So just depending on where the impact is, like it's the velocity is just perpendicular from like the distance to the point to where the impact happened.
Well, it's more like if we've got, most of these problems we've done have had a pin, right?
Yeah.
You know what I mean? With this pendulum. So then what you said is true. But we actually end up doing this stuff for, you could do it for two things that are free, like two cars. Actually, we could actually extend our vehicle accident reconstruction stuff to look at two cars that were hitting like this, right? That were off a little bit, but we didn't end up going to that. So the two types of problems we really have talked about were ones like this, where you have something hitting a pendulum, and then the problems where you had like the SUV, where it's a single body that's hitting a bump or whatever. And then we some moments about that bump. Does that make sense to you?
Yeah, I think so.
Okay, good. Okay, more questions.
Hold on, I have one. It was about this problem, I think. So I when I took this quiz, I'm pretty sure I messed up pretty bad. So I was just hoping maybe we can go through it a little more and try to figure it out.
Okay, have you had a chance to look at the solution yet?
Yeah. I also have the similar one that you were talking about earlier that we did in class on the one with the bullet hitting the block.
Uh-huh.
I was gonna ask about that one too, just because I have it in front of me.
Okay.
So I'm just really confused about the whole impulse momentum thing. So sometimes I get the whole eyes confused. So I was just hoping maybe we can just go through step by step so I can help figure it out more. Because every time I've done every example to study for impulse momentum so far, and I keep getting them wrong.
Okay, do you have it a little more? Because I kind of just did that with. You might have joined in late. I mean, we just did this guy here.
Yeah, I joined in late with that one, so I don't know how you got that whole first part. I get the last part, though. Okay, so really the first part's the exact same thing, right? So what you have to do for these, and here you can see the diagram, right? So essentially the first thing you have to do is figure out, okay, what point am I going to sum moments about? And if I have a pendulum type of setup, which is half of the problems we've done, then you sum moments about wherever that pin is. Can you mute yours for a little bit, Daliana? There's a little bit of background noise. Sorry, I'm at the library.
Yeah, no, I understand. I'm just trying to make sure that, because I'm recording it too, so I want to make sure we get decent here, and then you can go back and review what we talked about at the beginning of this as well. So as long as that recording's working, which hopefully it will. So basically, we have to figure out, okay, what point is best to sum these angular momenta about, and then after that, right, then it's kind of critical to draw out these diagrams. So you had said you kind of got this second part, right, which is all right here. So that made sense to you. Well, really, it's the same thing in the beginning as well, but for these, a lot of times we just have something with some initial linear momentum, right? So we could have it could be some sort of a bullet or something coming down like this at an angle, right? So to figure out the angular momentum about point O, we can either try to figure out what this perpendicular distance is, and sometimes that's not too bad doing the trig. But the other thing we can do is just an R cross MV, okay? Or I can look here and I can say, well, if I look at this guy, I know what the X component is, right? So I've got some sort of X component going there, and then I can figure out what this distance is there. Okay, so I can do this vectorially like you used to do R cross F, or you can do it kind of with scalars and perpendicular distances, which is force times a perpendicular distance, right? But in this case, instead of force, we're doing linear momentum. Okay, and everything could have this stuff to begin with. So I could have, like I said for here, for the rod, right? So for the rod part, the rod could be swinging around down through like this way and hitting it like a pinball or a baseball bat or something like that, right? And so each of those could have an initial one for almost all the problems we've worked, except for the one you did Monday in class or in the catapult, right? I think in that case, didn't this catcher deal, I think had an angular momentum going around like that, and then the ball was falling down to catch it. Okay, so everything could have an initial IG omega, an initial MVG dr. Okay, and then you got to remember too that I could just end up, if that's a fixed axis of rotation, I can combine those two to have like an I O omega. I don't have to, but that's done a lot. Sometimes it makes it easier for some people to visualize. So either one of those approaches is fine. Okay. Then you have to look at your impulse diagram, which it looks like we've erased because we made room for other things. And in most of these cases, right, since I chose right here to some moments about, I chose wherever my pin was, those typically end up being 0 because there's no perpendicular distance, right? There's no moment about that point. And then when I look at my system that I've defined as being both of them combined, then the impulse from the ball and the impulse from the pendulum end up canceling one another out. Okay, so Daliana, what
okay, so you said that I can do the IO omega instead of that whole box equation right there, like the whole IG omega plus MVD?
Yeah.
Okay.
Because remember, this, what is V via the center of the rod?
Yeah.
Right?
So
that's just L over 2 omega, right? And then D perpendicular is L over 2, right? So L over 2 squared, right? I've got a mass here, and then I've got L over 2 squared. That just is a perpendicular, that is a parallel axis theorem, right? Because this is equal to IG.
Oh, okay. Yeah.
Times L over 2 squared, right? That is IO, and that's times omega. So just like the quiz. So I did that quiz problem a couple times ago just to get you thinking in that.
Okay. And then the IS is 0 in the second half of that whole equation because it sticks to the blocks, and then you just have to do the IG for the entire block.
Well, so the IS was a sphere.
I mean, rod, sorry. Yeah.
So this would be for the sphere that's hitting it, right? So what we had there is that the sphere didn't really have there's two ways here. One is it doesn't necessarily have its own spin. So if there's no omega S, this term here goes to 0. And the other thing we've done a lot of times is we modeled that as a particle. So if it's a bullet or something that doesn't have much radius, then the IS goes to 0.
So it's 0 in the first part too because it's not spinning initially, or? Right. Okay. Okay, I thought it was.
So in that case, the omega, like for the problem we did on Monday, right, that you worked out, that omega S was 0 initially, but it wouldn't be afterwards, right? Because afterwards the sphere is going to be rotating kind of downward.
Yeah. Okay. Okay, I get it.
Cool. All right, Abdullah, I think you didn't get a chance to ask another one yet, if you had an original question.
Well, for one, I kind of came to watch, but also I had a couple questions, but you kind of answered some of them.
Okay, good.
Yeah.
I just want to make sure everybody had a chance. So just whoever now, Sonia or Sydney or Daliana, would you guys have some more questions?
I have one regarding one of the particle problems that was posted in that Word document.
Okay.
It's the one with the car on a bank. And I just wasn't sure how you would know which way to choose your force of friction.
Okay, hold on. Let me bring that guy up. So these are on the review problems that I posted, right?
Yeah, the ones that had a link to the website in the same document.
Yep, gotcha. Okay, so particle problems and a website, right, is what I call it. Okay, let me open that guy up. Okay, so this is the second one with the freeway ramp one?
Yeah.
Okay, yeah. So there, what you'd want to do is you know, for the question that you asked is, how do I know which direction the friction's going? Let me see for this whiteboard if I can add a new page. It looks like not. Hold on a second. I'm just trying to think of what I want to do here. Let's see. Can I select things and then delete? Okay. Sorry, I should probably do a little training on this newer program, because the old one I really like, because I could you know, I could just add new white pages and then go back and forth, and then I could let me see if I don't think I can copy and paste this picture, but maybe I can. Control V.
Why don't you just use the old system?
Because they don't have it to it. It was Blackboard. Illuminate it was called. Let me see. Can I paste? Yeah. So it's a cost saving thing. And not enough people were using the old system, I guess they decided. So, but good question. Plus, I lost all my old recordings. Okay, so I can't copy and paste this. This thing. I apologize for that. The figure. So let me just double check one or two more things real quick. Can I do that? Yeah, it doesn't look like it lets me paste. So what you get instead is my scratchy drawing. So basically, when you look at this thing, it's got see, draw. You know, it's got a car that's on this. So there's my model of the car, and then this is my beta, right? So it's going around the freeway off-ramp that's circular with a 60-meter radius and a bank of beta equals 20 degrees. So you're trying to increase it with an A equals, one second. Let's see if my pen comes back or not. So A equals 0.1 times D. Right? So we have 0.1 times D there. So when I have to figure out, okay, because I got to draw my FBD there, because if I'm looking at this static coefficient, if I go faster, right, then what's going to end up happening? Which way do you think the friction will end up keeping me in the ramp there? Does that make sense?
Okay, so downwards?
Yes.
Like in towards the incline.
Correct. So the faster I go, right, then I need to have something to accelerate me in towards the center, right? So as I go faster and faster, then something's got to accelerate me in towards the center. So the curve. So it ends up being the friction, right? The friction that's going this way. It's that component of the friction that actually accelerates me in towards the center.
Okay.
Okay. So if I stopped, right, then if I was on a really slippery bank that was either ice or something like that, then maybe I might start trying to slide that way.
Okay.
Right. And what would oppose that motion?
It would just be the opposite.
Yes. Yeah, the friction going up. Now, all that being said, it should end up when you do out your math, right? So if you do your equations of motion and you assume friction's going one way, right, it should end up that you solve it out, and let's say you, for whatever reason, had decided to guess that friction was going up and to the right. Well, you should get a negative number when you solve this problem for friction.
Okay.
Which means, I messed up on my guess, so friction's actually going this way.
Okay. So in this problem, would you solve it for friction, or do you solve for like the actual velocity and then the velocity that you would get with the force of friction that you have, and see if that's like greater than? Because that's how I sort of looking at it.
Yeah, I mean, so I would try to figure out, okay, I mean, you're right. There's two ways you could kind of do it. You could try to figure out, well, what's my what's my velocity when I get at the very end, right? And then I could check to see, okay, does that mean and that might be what I did, because I just asked you, does it make it through, right? So I would probably look and see, okay, what's my velocity at the very end of the curve? Right, and then I would check that. What friction force do I need at that point?
Okay.
You follow what I'm saying? And then once I check that friction amount, right, then I can say, okay, is that bigger than or less than my mu sub s times n?
Yeah. Okay.
Okay, so it's a little bit almost like, if you're checking to see if you're rolling without slip. You see, can I get that much friction out of my surface?
Okay. That makes sense.
Good. Did any of you guys check out the simulation modules yet? The Utah State stuff, that number 3 thing?
I looked at one of them, but pretty quickly.
Okay. I don't know if did it seem useful or just so-so?
Yeah, it looked useful. Like, I plan to go back and look at them more.
Okay, good. Yeah, and I'm not quite sure if I should make those earlier, but sometimes it's kind of nice just to have a last kind of review thing, you know what I mean? So, okay, Sydney or Daliana, Abdullah?
I had a question about this problem. I worked it through, and I was wondering if you had an answer for it.
I probably do somewhere, but I don't have it handy.
Okay, no problem. I just wanted to check if I actually did this right.
Let me just double check and see if I have it on my thing here. Approach. Sorry, I'm just trying to see if I have it. I don't have it handy. I'll see if I can track that down, though.
Okay, that's fine. Thank you.
Sure. Okay, more questions. You guys feel all right with your catapult? You know if you've made any mistakes, that you figured them out yet?
Yeah, well, I do have a question, I guess, about that. So, like, ours was off, like, short a little, but we're pretty sure that at least the calculations that we put into the Excel sheet are right. But we're thinking it was probably, like, our rubber band measurements that were off.
Okay.
Because, like, I mean, just kind of comparing with other people, we're pretty sure that the calculations are right, but we kind of had quite a bit larger work done by the rubber bands.
Okay, so there's two things. One, you could have something off. You should maybe just double check with that in your data.
Yeah.
But I did also, things are still over in the library. If you want to did you keep your rubber bands?
I'm not sure. I'd have to ask one of my partners, but I think so.
Okay, so if you kept the rubber band, you could do just one more. You could go over and do one more test.
Okay.
Just with those and say, oh, look, I think these rubber bands, we might have missed it a little bit, and depending on how much you want to do, you could recalculate everything according to those, but that's probably a bit much work. But you could say, look, we underestimated what we think the energy is. We think the energy would actually be about 10% more, so we think it would be high. You know what I'm saying? Does that make sense to you?
Yeah.
So, I mean, the thing I kind of like about this is now you have some at least somewhat proof of, here's your answer. It's what happened there. So now you have to think of, just like in your job and engineering world, why did things not quite work out like I thought they would?
Okay, so if we kind of provide an explanation of that and possibly some proof with it, would that be kind of enough in that section of the memo? And
the people who were a lot farther off, I mean, you guys actually did pretty well. There were only, one or two teams that kind of were more than 25% off in their calcs, right? So, if you're within 10%, you don't have to do quite as much explaining.
Yeah, I think it was like 13% or something.
Yeah. So, in there, you may be able to come up with some decent explanations of why. So,
okay.
Yeah.
Okay, thanks.
Because I'd much rather have everybody hit it, all the time. It would be more exciting for everybody too, I think.
Yeah. Okay.
More questions?
I'm going to be signing out, so thank you.
Okay, Abdul. We'll see you tomorrow.
For sure. Bye-bye.
Bye.
I will be leaving too, so see you tomorrow.
All right, sounds good. Thanks.
I have a question.
Yeah, go ahead.
So I was just doing the problem that with the bullet and the block that you were talking that we did in class. I think it was on Friday.
Okay.
So I have two unknowns, and this is omega and velocity for the final ones. Do I put velocity in terms of omega r, or because I'm solving for v, so I don't know if I should do that or not.
Well, I mean, in the end, you could do either one, right? Because you really end up doing, gosh, my pen.
Then I can plug it in and then solve for v later.
Correct, right? Because for here, especially with the A there, right, that you've got the V of G, and if you look at the solutions we did, right, we said, well, the bullet mass is basically negligible. So really, in this case, VG is equal to VA plus omega cross R, right? And this is true whether it was right before or right after the impact, right? And in this case, the R is from A to G. Okay, so then whichever one you end up solving for, right? I mean, so VA goes to 0, and then essentially when this goes down to scalars, it's just going to be that the velocity of the center, G, is going to be equal to whatever that distance R is times omega.
Okay.
So whichever one you do, you can always use this relationship in the end to solve for the other one.
Okay. What about the final velocity of the bullet?
Yeah. So for there, as we had mentioned before, you can either do it the same type of thing, but in this case, you've got a square, and the bullet's like right there, right? So then you can figure out how the bullet's related to this guy, right? You know what I'm saying? Does that make sense?
Yeah.
Or
like we would use the velocity that you said that was perpendicular to that line.
Yeah. Right, because it's the same exact equation as you use right here, right? Except for now it's velocity of point B.
Okay.
But the other thing you can do, Daliana, is what is the mass of the bullet?
45 grams.
Right, and then what was the mass of the plate?
9 kilograms.
Yeah,
so we can just take it out.
Yeah, so what you can say is, I try not to say 0, and I may say that at times, and I try not to say kind of take it out. I usually try to say things like the mass of the bullet is negligible compared to the mass of the plate.
Okay.
Right? So if you're doing a test and you're in a rush, then one way you can do is just say like either MB and then do like a couple of less than signs. You know what I mean?
Yeah.
Then MP, or you could do MB is approximately 0. So I would never want to do like MB equals 0.
But for the initial part of the equation, we wouldn't want to take that one. We wouldn't want to make the mass like negligible for that, would we? Or just
no, because the velocity is so high.
It's too high. Okay.
Yeah, but the block it absorbs so much of that velocity,
Yeah.
and now it's going to have the same order of magnitude of velocity as the center mass of the block. Right, that's what the key part is now the two V's of the block and the bullet are about the same.
Okay. Okay, I get it now. Thank
Good.
you.
You're welcome.
Yeah, no more questions. I'm gonna go head out. I'll see you on Friday.
All right, darling. Are you skipping class tomorrow?
I mean tomorrow. I thought it was Wednesday. I'm sorry.
No worries.
Dead week's killing me.
I know what you mean. All right.
Bye.
See you tomorrow. Bye.
Cool. I just wanted to hear her last question. I think I'll
Okay.
go too.
All right, Sydney. Have a good night.
Thank you. You too. See you tomorrow.
All right. Take care.